Hello guys, so we performed a simple simulation for fluid mechanics problem where we use the pump to increase the pressure of our outlet feed by 300 kilopascals, and then we evaluate the energy flow to the pump if 75% efficient. So from the simulation we found the energy flow to be about 0.00040184 kilowatts. And I gave you an assignment for you to do the simulation, not the simulation actually, to do the calculation analytically using the mechanical energy balance equation. So I want us to review that before we do another simulation problem, perhaps this time or the next video will be about friction losses and pipe fittings for that. So let's go over to what was required to be done. So we had the simple mechanical energy balance equation, change in P over rho plus the change in the average velocity squared over 2 plus the change in the elevation times the gravitational acceleration is equals to work shaft per unit mass minus the friction loss per unit mass. All this is expressed per unit mass. So we said that because we assume that the cross-sectional area of the pipe will remain the same, there will be no change in the kinetic term. We neglected it to be 0, and we also neglected changes in elevation because the pump hardly, because you're dealing with a positive displacement pump or a centrifuge pump, the changes in the potential term is negligible compared to the pressure changes. So we had the changes in pressure divided by the density to be equal to work shaft per unit mass if you obviously neglect the changes in the friction losses, because actually this was a simulation for the pipe. So we're gonna do a simulation for friction losses in our next video, and we will be around, so you have to subscribe and be ready for that. So we say the work shaft is positive when work is being done to the fluid by the system. And therefore, since I'm dealing with my work pump, I'll substitute it for a positive value, positive dWp by dm, and then I put this to the change in pressure over the density. So at this point, we have now to, because you have a differential equation, we separate the variables. The change in P over rho term will actually be multiplied by the dm term, because actually I'm dealing with an open system, it's a continuous system. So we are dealing with the rates. So the rate of the work pump will be equal to the change in P over rho multiplied by the rate of mass flow rate. And then obviously you can integrate that from 0 to work pump, because actually we're trying to evaluate the work pump, the energy needed by the pump to pass this mass to this pressure. So we from 0 to work pump, and then from 0 to the mass flow rate, which will evaluate the pump on. So we have the work pump, the rate was applied to the work pump will be equal to the change in pressure over the density multiplied by the mass flow rate. And then the mass flow rate is actually equal to the density times the volumetric flow rate, which implies that my density and density will cancel. So we have work pump is equal to the change in pressure multiplied by the volumetric flow rate. So obviously now we substitute the values, and from our simulation at our pressure was 300 pascal, sorry, that was an increase in pressure, and our volumetric flow rate was about as you can see is about 0.00102996 meters cubed per second. So we substitute the value. On the next page we multiply by 300, we have an energy needed to be 0.30088 watts. Now if our pump was 100% efficient, this would mean that we needed about 0.30088 watts supply to the pump, but actually it's 75% efficient. So from that we have the rate of energy that will be supplied to the pump by the utility stream would be actually 0.4001184 watts, which is 0.004001184 kilowatts. Actually, this is what the simulation program gave us, as you can see. So that's actually what it's an important characteristic for simulation programs, because you can actually perform energy balances and mass balances of complex systems faster. So if this video is helpful, please make sure you subscribe and like, because from here things are going to get interesting. Thank you.